Early on in my career, once I'd gotten beyond the basics, I really started trying to understand more about software engineering. At one of my early jobs, I worked on a large legacy codebase. I think at that point the project was already 8 or 9 years old and had been upgraded from web forms to MVC. I know this as I had the lovely job of converting all the ASPX files to CSHTML. In the actual logic, I was presented with huge classes with hundreds of methods and properties. Some of these classes have thousands of lines of code. I also came across interfaces being used for everything, and more often than not, these interfaces were really large too. I found the code really confusing and difficult to work with. I would often just sit at my desk, staring at closed window blinds because I wasn't allowed to open the window blinds, thinking, why the is this so complicated? In the end, I put this down to my lack of experience. Looking back, I should have listened to my instincts as things could and should have been done differently. So after many months wrangling this code, I wanted a new job. No surprise there. The one I was after needed test-driven development, so I started to teach it to myself. And it was whilst learning TDD that I came across the solid principles. It was like a little light bulb blinking on above my head. Suddenly, I was able to solve all those niggly things that just didn't sit well with me in that humongous code base. It was awesome. I definitely wanted to learn more. So I started reading this book, Beginning Solid Principles and Design Patterns for ASP.NET Developers by Bipin Joshi. It really helped to put the concepts into the context of C#. This book has examples written with .NET 5, so it's a little out of date, but the principles and patterns discussed are timeless. In fact, none of the principles and patterns I'm going to tell you about are new. Many were pioneered in the 70s by really clever people, and they keep resurfacing every few years in new guises. So you might have seen or read about solid principles before, but if you're here, it's because you're still a little bit unsure. I'm going to explain them in a pragmatic rather than dogmatic way. So let's get cracking. S stands for Single Responsibility Principle. What this means is that a piece of code or software should do one thing and do that one thing well. This can be applied to something as small as a single method or as big as a microservice. Is that an oxymoron? Anyway, this doesn't mean that a method, class, or service can only do one job. It means that everything it does is closely related and belongs together. A good way to describe this is that it has high cohesion. Let's take a look at some code. Looking at this method, it's doing a lot. It instantiates an HTTP client, makes a GET request, deserializes the response body to a list of type string, then leaps over the list and prints each item to the console after making it lowercase. Whew. If any part of this code fails, we won't know where that failure is coming from. Is it the GET request? Is it the deserialize? Is it something in the loop? Is the list null or empty? We have no idea. This method is just doing too much. Let's fix it. I would say that it has two main functionalities, so let's split it into two methods. First, I'll create getList, and it will be responsible for the HTTP call. I'll make a private property called list to store the deserialized list. Now I can make a method for the loop that prints the list, adding a quick check to see whether the list is empty and then proceeding to our loop. The doWork method will now call both of these methods. This may look like a lot of additional work for no real gain, but now each of the individual methods is testable. There is definitely more I would do to this code, such as a try catch around the HTTP request, and injecting the HTTP client rather than mewing it up. That's a responsibility I really don't want in my method, but you get the idea. Next up is O for open close principle. This means that a method or class is open for extension, but closed for modification. This was definitely the principle I found hardest to grasp, as what does that even mean? Well, let's say, for example, we have a service and we have a whole host of unit tests written for it, and it's deployed in production. If we start fiddling with the code in the service to support a new feature, we could break production and we'd have to update all of our tests. And sometimes you may not even be able to fiddle with the code as it's from a third-party library and all locked away. There are numerous examples of how to adhere to this principle, including polymorphism, which you're probably already doing. Let's take a look. First, you can see an example of polymorphism with this abstract meal class. Both the salad class and the lasagna class extend the functionality of the meal class without modifying it. But how can we add an additional method to one of these classes without modifying them? One way is to do this with extension methods, and it's something I use all the time. Let's add a method to salad. I need to make a static method that returns salad, given a name, say add utensil, then the first argument must have the this keyword followed by the type I'm extending, in this case salad. Then any additional arguments if required. So I am going to pass in a utensil string. Lastly, I need to return the salad object. I now have access to the utensil list on the salad object and can add the new utensil to it. I can also do any other logic I need. To use it, I can just call the add utensils method as if it were part of the original class, passing in a new utensil, like a spoon. We've added functionality without modifying the original code. That's all the open-close principle is. If you'd like to see how I use the extension method pattern to tidy up my program file, check out the video up there and I'll link it in the description too. L is for Liskov substitution principle. This states that every subclass or derived class should be substitutable for their base or parent class. This can be confusing, as what it really means is that any implementation of a base class should be substitutable for its base class and any other implementation of the base class. To dig deeper into what this means exactly, let's go back to those meal classes. If I have this method where I expect a salad and I call the add utensil method, this doesn't conform to the Liskov principle. Why? Well, if I substitute salad for its base class meal, you can see that it's not possible. The add utensil method is specific to the salad class, and that prevents us from substituting the salad class for the meal class or even the lasagna class. So how can we obey both principles?
Wait!
What? Let's think about the language I'm using here. Obey sounds far too dogmatic. These are not rules to be obeyed or violated, they're just guidelines. Let's try that again. All right. How can we satisfy both principles? Better? That will take quite a bit of refactoring, but let's go for it. First, I can get rid of the extension method for salad. Next, I need to create an interface called iExtra with a method called addUtensil. This time, I'm going to use the Decorator Pattern to extend the functionality of salad. The Decorator Pattern is the process of encapsulating one class within a second class, adding any additional functionality. To do this, I've created a class called Salad with Extra. This new class extends salad and implements iExtra. I can now add in the code from the addUtensil extension method. This gives us the same functionality as the extension method. Now I just need to rewrite the makeDinner method using generics, where T is any class that extends meal and implements iExtra. I can call the makeDinner method like this. To dogmatically satisfy the solid principles, I've had to write quite a lot of additional code. Based on your application, you'll need to make a call on how far you actually want to take the solid principles. Otherwise, you risk over-engineering your applications. In this example, I probably would have written a make salad method and a make hot dinner method, as it would have been far less work. I is for interface segregation principle, which states that no code should be forced to depend on methods it does not use. Ever seen code that looks like this? Me. This is definitely one of the issues in that big legacy codebase I mentioned earlier. This means that this class implements an interface with lots of methods it doesn't need. This principle is easily addressed by breaking interfaces down into the smallest chunks possible. In this example, the listActions class only needs the add and delete methods. The other two methods aren't implemented. To fix this, I can chop up the iAuditList interface into two interfaces like this. Now listAction only needs to implement iListAction, but classes that need to include all four methods can implement both iListAction and iAuditAction. Much better. Right, Last one. D is for dependency injection. No, wait. I bet some of you were thinking that. It's not for dependency injection. D is for dependency inversion principle. Although they are related, they are not the same thing. The dependency inversion principle states that high-level modules should depend on abstractions rather than low-level modules. In C# terms, we want high-level classes to only depend on abstract classes or interfaces rather than concrete implementations. Let's take a look at some code that doesn't conform to this principle. We have a higher level class called meal service, and it has a dependency on salad as I instantiate it within the constructor. This doesn't conform to the dependency inversion principle because I have a dependency on a concrete implementation of meal. Wait! What now? Something I do when I see the new keyword, wherever it may be, is to check that it's not creating a dependency I don't need. Good tip, thanks. So I could improve this implementation by injecting salad instead of instantiating it. This would decouple it a little, but it's still a dependency on a concrete implementation. Instead, it would be better to create a dependency on the abstract class meal. This makes this service a lot more versatile and strongly adheres to the dependency inversion principle. A good side effect is that it will make the code more testable as we can mock the dependencies. You'll often see this kind of implementation when using the repository pattern. You'll create an iRepository and inject that into your service. Then you'll probably only create one concrete implementation of the iRepository interface. This is an often argued pattern. Am I over-engineering by creating an interface for my lone repository class just to dogmatically obey the dependency inversion principle when, in reality, I'm unlikely to ever swap out the concrete repository class? I'll leave that for you to decide, but I will say having an interface means it's easier to mock or substitute in a testDB. Well, I hope this has given you a solid understanding of the solid principles. I think the main point to realize is that these principles are just a tool, not a commandment. Use them to write better software, but don't become dogmatic with them. I genuinely believe that learning design patterns and principles has made me a better programmer. But what about you? What do you think has made you a better programmer? Let me know in the comments down below. Thanks for watching. Bye!